Okay, welcome back to the second part of the lecture. So what we're doing is we're looking at the summation convention, right? And we had said the summation convention is essentially a shorthand to represent this kind of a summation, right? Okay, so and we had also said that the repeated indices may not be repeated more than twice, and that is to keep sanity within the kind of convention that we are trying to develop. So just to repeat, no index may be repeated more than twice in a term, right, in a single term. So something like AI, BI, CI, this is an incorrect representation. Similarly, if you want to write AIII, this is also an incorrect representation. Sometimes you might want to signify the actual value given by sigma II. So you might mean sigma 1, and what do you do in that case? So if you have to suspend the summation convention, then what you can do is you can do it in two ways. Sometimes people just write no sum, and or sometimes underline the subscripts, and this basically means or sigma 2 or sigma 3 or sigma nn, right? Okay. Okay, so going forward, we will note that from here onwards, we will restrict I to 1, 2, 3, okay, because we are going to be dealing with the 3 dimensions. So we have discussed the general treatment, but from here onwards, we will just make sure that we understand that I only takes the 3 values. Okay. So now we introduce one more important term, the Kronecker delta. This is a rather important term, and the Kronecker delta is a term which is usually written as delta and with 2 indices I and j, and it is defined as being equal to 0 if I is not equal to j, and equal to 1 if I is equal to j, okay, which means that, so this implies that anything like with a cross term like del 1 2, del 1 3, etc., or del 3 2, all these type of cross terms, they will all be 0. But the non-cross terms, which means there will be 3 in this particular case. Of course, remember that we are now restricting ourselves to 1, 2, 3 for I and j will be equal to 1. So the Kronecker delta is basically the identity matrix. So delta ij is essentially the identity matrix. Sorry, this is 0, 0, 0, 1. Okay. Okay, great. So let's say, so what is del II? So del II is, now we know it's sum over 1 to 3 del II, right, and it will be a simple scalar value of 3. Okay. Great. You can also show, and this is, I am just leaving it to yourself, it's a very quick exercise that show that del ij into aj is equal to ai. Okay. So, please do this yourself, and if you run into a problem, please let me know. Okay. This is an important result. This is also an important result, so we will maybe just mark it out. Okay. There is one more interesting term that you might have heard in this combination with regards to these tensors, and that is called the permutation tensor. So, the permutation tensor, okay, sorry, the permutation tensor, which is usually written as epsilon I j k. So, it has 3 index, and it is defined as epsilon I j k. Now, it can have 3 values, okay, and it is plus 1 in certain cases, it is minus 1 in certain cases, and it is 0 in certain cases. It is plus 1 when these numbers are in order. So, epsilon 1 2 3 or epsilon 3 2 1, sorry 2 3 1. So, this is 2 3 1 or epsilon 3 2 1, sorry 3 1 2, I am sorry, I made a mistake. So, here 3 1 2, and it is minus 1 for cases which is where you have gone in the opposite direction. So, if you are doing a 3 2 1 or epsilon 2 1 3 or epsilon 1 3 2 and 0 for all other combinations. Okay. So, just remember, it's easiest to remember. So, let us write down. So, you have 3 numbers, right? The subscripts can go from 1 to 3. So, if you want to think of a clock with these 3 numbers 1 2 3, then we are saying that if the numbers are in this order, that you go from 1 to 2 or 2 to 3 or 3 to 1. Okay. So, if you see 1 2 3, this first number, this is in this correct cyclical order. 2 3 1, 2 3 1 begins at 2, goes to 3, goes to 1. 3 1 2 begins at 3, goes to 1, goes to 2. So, if it is in the clockwise direction, you have plus 1. Whereas, if you have it in the order 3 2 1, so you have now gone anti-clockwise, then you will have it is value is 0. Then you have, if you begin at 2, then you go 2 3 1 3, which is this number, or 1 3 2, which is this number. So, then you have these 3 anti-clockwise combinations. So, it is minus 1 and 0 for all other combinations. Okay. So, you can so this is a very important variable that is often used in many cases, and again an important identity and an important identity in this case which you might want to sit down and prove is epsilon I j k multiplied by epsilon I L m is equal to delta j L delta k m minus delta j m delta k L. again something I am sort of leaving out for you to take a look. We will use these a little bit, but our basic aim why we were doing all this was to look at tensors. So, these tensors, as we have already figured out, they are basically mapping of one vector into another vector when the dimensions are finite and when you have an Euclidean space. So, for us the space of all column vectors of a given rank, they are an important is a very important parameter. Rather I should say okay, maybe I should reword that. So, the space of column vectors with a certain given dimensions, let us say number m dimensions, that becomes a very important vector space essentially, because you can see that all our work will be dealing with vectors which do have an arrow, which can be thought of as an arrow and direction, and that is why we are discussing these tensors, and hence this tensor is going to be very, very important to us. So, now coming back to the idea of tensors, a tensor of rank R basically is a quantity having n to the power r components in n dimensional space. So, a tensor of rank R is a quantity having n to the power r components in n dimensional space. So, you started off with an n dimensional space, and tensors defined in that will be will have n to the power r components. So, if you have a dimension, if you are working in 3D space, so in 3D space, which is where we are going to be working with, if you have a tensor of rank 2, then how many components will it have? 3 to the power 2, right? It will have 3 square components. Okay. So, I run out of space. So, basically we have 9 components, and we will see that there are in the next chapter, which is going to be on kinematics, where we are going to encounter stress, strain and strain rate. Those are all tensors with 9 components. So, a tensor of rank 2 is also sometimes called a dyad, that is it can be written as Aij. So, if it has 2 components, then tensors with 2 component with rank 2 can be written as Aij for us, right. So, this can represent tensor of rank 2, which is why we were spending so much time with all these different indices and index notation, right, because we are going to be dealing with things like this. And by the way, a tensor of rank 1, so you can now think of a vector as a tensor of rank 1, and you can think of a scalar as a tensor of rank 0. Okay. Okay. So, a couple of more things with regards to tensors, and that pertains to the transpose. So, the transpose of a tensor. Okay. So, this is a different color. So, the transpose of a tensor okay, this is O, sorry, this is the transpose of a tensor is given by, and let's say we write the tensor as, so I'm just going to write this side first. So if you write, if you say you have okay, so let's say the transpose of a tensor. Okay, let me write on this side, that will be easier. So let's say T is a or A, I will be using A. So I'm sorry, we are just a little bit messy right here. So let's say we are using A. So let's say we have I, J all the way to K, right? Then the transpose is a tensor such that now you have reversed this direction. Okay. So then the transpose, the first index of the transpose will be the last index here, and then the first index of the previous transpose, that will become the last index here. So this will become K J I. Okay. So this is the transpose. You are very familiar with this, right? So if it is a if the tensor only has I J, then this is very straightforward for you to figure out, which is A J I, right? Obvious. And related to this idea, there are two more ideas which are called the symmetric and the antisymmetric tensors. And symmetric tensors, if the transpose has a property that the two tensors are equal to each other. So a symmetric tensor is such that when you do the transpose, the A transpose is equal to A, if then tensor is symmetric. And in an antisymmetric tensor, if A transpose equal to minus A, then tensor is called antisymmetric. Okay, so we will come to this when we look at the stress tensor. We will see that the stress tensor is actually symmetric. So even if you take a transpose, you end up getting the same values. Okay, so the stress tensor is symmetric for certain types of materials, which includes non-Newtonian Newtonian fluids. So water and air, they are all fluids such that the stress tensor is symmetric. But that need not be. There are other types of fluids which stress tensor is not necessarily symmetric. Of course, that is does not fall within the purview of this particular class, but there are fluids like that as well. Okay. Now, the reason we were discussing all this is we are going to be dealing with stress, and we are going to be multiplying it with other vectors. Sometimes we are going to be multiplying it with other tensors. So it is important for us to define the different type of products that there are. Now there are many different type of products one can be defining in this particular case, but we had started out with a very important product called the dot product, right? It was the very basis of our definition of Cartesian tensors, because it was an important required property of the vector space that it have a dot product, so that we can define the other ones. So the dot product, now also called the inner product, the way we had defined it was such that, let's say you had two vectors. By the way, I have just realized this at many places. Have I dropped off the? So my convention is that if the convention that I want to keep is, if I am writing it in the index form, then I will not put that bar, because the number of indices is enough to indicate whether it's a vector or tensor. But if I am not doing it, then yeah. So okay, I hope I'm keeping my okay. Anyway, I hope I'm keeping I'm being consistent throughout. So when I'm not writing it in the when I'm okay. Anyway, let me just get it here. So I'll just qualify it here. What I meant. Okay, so what I'm going to do, and please let me know later on if I missed this. When I'm not writing it in the index notation, then I will put a bar over it, over the letter, to indicate whether it's a vector or tensor. But when I'm writing it in the index form, then I will drop it. Okay, that's what I'm just trying to do. Anyway, okay. So now we had started off with this very important definition that the dot product of these two vectors is basically this quantity in index notation, right. So now let's see if we can define dot products for other cases. So let's say you have a vector and then you have to do a dot product with a tensor. Can we define it? So, well, what we will do is we will just keep the same exact format. Now, this quantity B has two components, right. So, what I will do is I will just say I into j, and this becomes my definition of a dot product between a vector and a tensor. And I can go on using this rule to just keep on making this more exhaustive. So, if I have initially if I have the first one, if that is a tensor, then my rule will become Aij into Bj. Similarly, if I have a vector, a tensor, a dot product with a tensor, then it will be Aij. In index notation, this is like this. So, you can already see the benefit of index notation, right. Here, this is equal to what? This is equal to A1 B1 plus A2 B2 plus A3 B3. So, the index notation allows me to shrink this entire thing into this really simple notation, whereas you can see that this quantity is now going to be a vector, right, because I is a repeated index here, so it has to be summed over that, and j is a free index. Okay. Similarly, here j is the repeated index, I is the free index, and in this case j is the repeated index and I and k are the free indices. So, you can easily understand what this multiplication is leading to. Now, there is one more type of multiplication that is defined for especially for tensors, and it is often this defined by two dots, and this is defined as this. If you have to write it in index notation, then both I and j become repeated indices. Okay. And from this definition, you can easily see that if you were to do this as a transpose, then this is Aij and this is Bij. Right. Great. So, this does help us quite a bit, because very complicated expressions have now become compacted and much smaller with the help of this index notation. So, the index notation is extremely helpful to us. Right. Okay. So, now we are going to encounter the one other important thing before we go on to some of the theorems will be to look at some of the important operators, including the gradient operators. Okay. So, operators. some important operators that we are going to encounter again and again, and one of them is the del operator. Okay. So, the del operator in Cartesian coordinates. Now, the del operator by itself, so this operator is defined as del x I hat plus, so it has to operate on something. Okay, just a second, just 1 second. Let me, okay. So, the del operator has to operate on something, and we are not told you what, but the operation is where I hat is the unit vector in the x direction, then del y of whatever we are operating on, j vector plus del z of whatever we are operating on multiplied by the k vector. Now, sometimes it is very much easier to understand operators if you pretend that they are also vectors, okay, which is why I have already added this hat, this bar over it, because although it is not a vector, but pretending that this is a vector can be actually very helpful in memorizing or remembering how the vector really works. So, let us say you have a vector field f, so let us say you have a vector field f, then the operation of this vector, or in the sense of a, when it is used as in the sense of a dot product, then it is also called divergence. Then divergence of f is, and it is often written as div. Div starts with divergence. Divergence of f can almost be thought of as, if I have to pretend that this nabla is the delta operator is a vector, then I could just write it in this form, right. So, I pretend that this itself is a vector, this is obviously a vector, then I write the divergence as a dot product of two vectors. Now, I have already told you what this expression looks like, the delta operator. So, given that you already know what this is, and f is obviously equal to, so this here is obviously equal to f1 I hat plus f2 j hat plus f3 j hat, let us say in component forms, sorry, k hat, sorry, f1 I hat, f2 j hat and f3 k hat. Then if you know this, then it is really straightforward for you to write down the answer, right. And this quantity now is a scalar quantity. Similarly, there is another important quantity called the curl of a vector field. And if you again have f, say, so we have the same f, and if you want to take the curl, then the curl of f can be thought of as so by the way, you don't have to include this term. This term I'm doing it deliberately, this hat, to sort of give you the false notion that this is a vector. It is not exactly, but it almost behaves as if it is one. So even curl can be thought of as a cross product of these two vectors, then this quantity will be equal to, we know how to write curl, right. So again I am going to pretend that this is being written in Cartesian coordinates. Okay. So if I have to write the determinant, do you remember how to write the curl? I will first write down the first terms for the first vector involved in the curl operation, and then I will write down f1, f2, f3. I hope you remember how to open this up. This should be del f3 del y minus del f two, sorry, wait a second, del f2 by del z I hat plus del f1 by del z minus del f3 by del x j hat plus, okay, there is one more term. Okay, so I've run out of space, so I'll leave that to you. Okay. Now the gradient field, which is another important operation concerning this del operator, is the multiplication of the del operator with a scalar quantity. Okay. So the gradient operator, or the gradient field rather, sorry, it's no longer an operator, the operation has been done. The gradient field is the multiplication of del operator with a scalar quantity. So this del operator on f is del f by del x I hat. This is rather straightforward for you to remember now, right. Okay. So the consequence of treating this as a vector, okay. By the way, I'm just I included this hat just as a mnemonic. So now that I've illustrated the purpose of it, I can just go back and delete all these. Okay. So I'm going to just delete this part. Oh yes, sorry, it got too much deleted. So the consequence of treating these operators as vectors is that certain results become very self-evident. Okay, so some results, oh man, some results become obvious. And example, if you have the curl of any gradient is always 0. Okay, so curl of any gradient is always 0. So if I do this particular operation, this is always going to be equal to 0, because I am multiplying, let us say, this vector with or cross producting a vector with itself. the scalar quantity can just be thought of as a multiplying factor. So then this will be 0. I encourage you to please go ahead and do this yourself algebraically and prove it. Okay. Similarly, the divergence of a curl of a field is also 0. So, similarly, operations like divergence, let us say, of a curl. So, let us say you have the curl of a vector field and then you take the divergence, this is going to be equal to 0, and this is always true. Okay. Finally, the Laplace operator can be thought of as del operator's self dot product. So, you have this quantity is basically often can be thought of as this, and once you, since you are already used to, this is rather straightforward, del y square plus del square f del z square. Okay. Oh, I didn't realize I've spent quite a bit of time. I had promised you the answers. Okay, so we have already taken up a lot of time. What I will do, I promised you the answers to those other two problems. So I'm just going to write them out and give it as a handout, because I didn't realize that I've spent so much time here. Okay, so I'm going to end the class here right now. Okay, thank you.